All right, in number 28, we see a ladder leaning up against a wall, and I think I know immediately without reading any further, this is probably a related rate problem. So we've got a 15-foot long ladder. Now, it's important, guys, to realize that distance then is fixed. The length of the ladder does not change, so we can put a constant right there and not a variable. Rest against a vertical wall. The bottom of the ladder, okay, got it, and the ladder, yep, here we go, is sliding down the wall. So this quantity right here, everybody, is a variable quantity. I'm going to call that h for the height of the ladder. And what they're telling us right here, guys, we were given that the derivative of h with respect to t, the ladder sliding down the wall at a constant rate of 2 feet per second. So that's the rate at which h is changing. But of course, and this is important, I bet one of the wrong answers deals with this concept, h is decreasing over time. The top of the ladder is sliding down the wall. That means that derivative is actually negative 2 feet per second. And I'll bet a lot of us just put a positive 2 right there. Okay, at what rate in radians per second is the acute angle between the bottom of the ladder and the ground changing? So we're talking about this angle right over here. I'm going to call that theta. What rate is that changing? At the instant the bottom of the ladder is 9 feet from the base of the wall. I'm going to call this quantity down here x, everybody. And x is actually growing as the base of the ladder slides out away from the wall. And what I think that means is that theta is actually decreasing. So I'm expecting a negative answer, which again means if I had to guess right here for the rate at which that angle is changing, I think I can already cross out D and E, because I think just by thinking about this problem logically, as the top of the ladder gets lower, theta needs to be getting smaller. Anyway, so what we want to know, everybody, is the derivative of theta taken with respect to t at the moment when x is equal to 9 feet. Now, what's interesting about this problem here is they've given us an x value for when to evaluate this, but we don't know the derivative of x with respect to time, and we don't want to know the derivative of x with respect to time. So I think I know where this is going, but let's let it play out. What we need first, everybody, is an equation that relates h with theta. And the way we're going to do that, what always relates a side length with an angle in a right triangle, is trig. This looks to me, guys, looking at theta, like this is going to be a sine problem. The sine of theta, opposite leg over hypotenuse, is going to be h over 15. Okay, got it. Then I think we're going to go ahead and take the derivative of both sides with respect to t. So the derivative of sine of any angle is cosine of the same angle times d theta dt. That's going to equal, now h over 15 is a linear function. You can also think of it as 1/15th h if that helps you out. And the derivative of a linear function is always just its coefficient. So 1/15th, but there is a dh dt that needs to get multiplied right there. Okay, so what's going on, guys? We know the value of dh dt. That was right here. So on the next line, my right side is actually not that bad. I've got a 1/15th multiplied by dh dt, which we know is a negative 2. On the right side, we're not supposed to know what d theta dt is because that's what we're trying to find. But right here is the tricky part to this problem, everybody. In this case right over here, they're asking you to come up with the cosine of angle theta. Now, what's hard about this, I bet a lot of you got here and then got stuck, we don't know the value of theta at the moment when x is equal to 9 feet, and to find that, this is not a special right triangle with a short leg of 9 and a hypotenuse of 15. So you're not able to just figure out how many degrees, or actually it would be radians in this case right here, because they said radians per second. You're not able to figure this out without a calculator. But what you can figure out, even though we don't know what theta is the big picture right here, cosine of theta. Now, like I said, they didn't give you a special right triangle, but they did give you a triple, everybody. And this, I love this skill from geometry, and people sometimes forget it. What we're dealing with here, guys, if I divided something out from a 9 and a 15, they're both divisible by 3. This is a 3, 4, 5 triangle being multiplied by 3, everybody, which becomes 9, 12, and 15. Now, if you thought to check that, I bet you could have done this one on your own without a calculator, but you end up with big numbers of what, 225 minus the 81, you get a 144, and there you go. Your life is a whole lot easier if you know your geometric facts right here, including Pythagorean triples. So at the moment when x is equal to 9 here, guys, h is equal to 12. But now I feel silly because I didn't need that at all. I was so proud of myself. Duh. Cosine, everybody, is adjacent leg over hypotenuse. My mistake. So here's your theta. Your adjacent leg at this time is 9. Your hypotenuse is 15. You didn't need that 12 at all. Okay, so the cosine of theta is 9 over 15, which will simplify to make 3 over 5. So the point I want you guys to take from there is that even though we're not able to figure out what theta is, how many degrees or how many radians, you can still come up with the cosine of that angle. All right, guys, and now from there, we should be able to do the rest of this problem without too much difficulty right here. Okay, here we go. Let's see. So d theta dt then is going to equal, that's a negative 2/15 right there, and then we'll multiply by the reciprocal of 3/5, which is 5/3. So what happens here, guys? The 5 and the 15 cancel, leaving you a 3 on the bottom, and we're going to end up with negative 2/9 for d theta dt. Hopefully that is one of the options right there. It is, and it's A and 28. Yep, that is the right answer for that problem right there. So that's number 28, a good review of related rates.